Implication, okay, which is the next part of our logic unit. So we're looking at a relationship between our propositions P and Q such that P implies Q. So we might write it like this in with our symbology. P implies Q. It actually is a compound statement which is basically equivalent in regular English to if something then something else. It's an if then statement. So implication is a compound statement with the connective, that implication symbol, okay? And we can also talk about what's called implicative statements, and they follow the if-then form. So here's an example of implication using P and Q, where P and Q are the following. P, Vlad has a phone, and Q, Vlad can message his deputy. We can see propositions P and Q and their sentences, and they become statements once we determine their values, their truth values, true or false. So we have our implication defined to a degree, and we're looking at the two statements P and Q, and we sometimes called P and Q the following: antecedent for P followed by Q consequent. So we start with the antecedent and we terminate in the consequent. So when we construct truth tables for implication, there's a standard result, and we, with two propositions P and Q, we do it the way we're used to. So we need to look at true, true, false, false for P, and the same for Q. So we go true, 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 false, false, true, false, false. And you might have seen that I've left the column between them blank, and that's intentional. In fact, that's where I'm going to put the implication symbol. And you could have had a column like that, looks like this: P implies Q, and you could have done that after P and after column Q. Could have done it that way too. But have a look at this, see if you like doing it this way. Okay, so this, anything that goes into this column is the result of P implies Q, and there is a standard result, as I said. Okay, so true implies true is true. True implies false is false. I'm going to skip this one. False implied false is actually true. You might have been surprised to see that, or maybe not. And this one here, false implies true, is actually true. So we're going to explain a little bit of that. Now if we use our example before about Vlad has a phone, Vlad can message his deputy. Let's see if we can use that to explain to some degree this implication column. So Vlad has a phone, Vlad can message his deputy. So the first one's possibly the easiest one to grasp. So Vlad has a phone, so it, remember, is if Vlad has a phone, then Vlad can message his deputy. So this one's saying yes, Vlad has a phone, therefore Vlad can message his deputy. That's consistent, and so we give that one the true that you see. So the next one, Vlad has a phone, but Vlad doesn't or can't message his deputy. That's actually false, because that's not consistent, because the original premise said if Vlad has a phone, then he can message his deputy. Vlad has a phone, but he can't message his deputy, so that's false. So it's not consistent. Now I'm going to skip the third one again. This one here, Vlad does not have a phone, and Vlad cannot message his deputy, is consistent. Now this one here, perhaps the strange thing about it is that it has a value of true. Vlad does not have a phone, but Vlad does message his deputy. That's actually, as you can see, it is true there, but the reason for it may not be clear. Now, when you look at what we have here, it says that if Vlad has a phone, then Vlad can message his deputy. But it's not saying anything about if Vlad does not have a phone. This implication statement, if then, only covers for true values for P. It's only based on that. If P is false, we don't have to follow any particular passage. So if P is false, Q is always true. The original implication is only saying if Vlad has a phone. It's not saying anything about if we start off with the antecedent being Vlad not having a phone. That's not relevant. So it gets a true. Okay, so that's that true there. Another way perhaps of thinking about it too is that, was there a lie or is there some inconsistency happening? Okay, has someone done the wrong thing? The first one's obviously true. If Vlad has a phone, Vlad can message his deputy. He has a phone, he messages his deputy. Vlad has a phone and does not message his deputy, he can't do it. Well, that's an inconsistency. It's almost like a lie's been told. The third one, Vlad does not have a phone, but that's alright because the premise is only about if Vlad does have a phone. So that's true, no lie has been told. It is actually consistent. It's not inconsistent. And the last one is consistent. No phone, no messaging. That's consistent, that's true. It's not like any sort of lie has been told. So make sure you learn the pattern and the truth table for P implies Q. That's something you need to be fluent with. Let's look at another example. We've got quite a different sort of example. Now, we don't have to, this will work for R, but we'll just, that's real numbers if you've forgotten, but we'll just keep it simple. We'll look at just integer values for X to keep things simple. So we've got proposition P, X is greater than 3, or a number is greater than 3. Proposition Q, number squared is greater than 9. Now the following table is not actually a truth table, it's just a table with some sample values, okay? So the first column here is X. So let's say X is 4. X squared would be 16. Is X greater than 3? Yes it is. Is X squared greater than 9? Yes it is. So we can see a true happening there. And what about a 1? A 1 is greater than 3? False. 1 squared is 1. Is 1 greater than 9? False. So you'll see cases where we have true and false and false. Let's try another one. How about a negative? Negative 5. Okay. Negative 5 all squared is 25. Is X greater than 3? False. No, it's not. Is 25 greater than 9? True. So we can have in cases like this a false and a true. How about a false, a true and a false, sorry, in that order, true then false? Well, what could we have as examples of that? So have a think about it, where we have true then false. Well, the answer is no, it's not possible. If you've got something bigger than positive 3, there's no way, there's no examples we can supply that will give an X squared value greater than 9. So it's not actually possible. So it's kind of, in a way, shows that previous result we just saw above, where everything is true in here, except for the case of where we have true then false. That gives a false. And have a look here, true then false is not possible. So these first three, they're all valid, so you could call them all true. This one is not valid, it's false. So it's a little bit of a telling result. Okay, time for you to pause the video now and see if you can do this one yourself. And what we have is an example. If you do your homework, then you can go to the basketball game. See if you can turn that into symbolic language to do a logic, and then complete the truth table and see and check that it follows that pattern we've just established. Okay, so when you've finished, unpause the video. Okay, so perhaps you might have started with P and Q, and you do your homework is proposition P, and Q you can go to the game. And let's see how that works as a table. So the first one is you do your homework, you get to go to the game, and that's consistent, so that's true. You do your homework and you're not allowed to go to the game. Wow, that's betrayal, so that gives a false. Alright, it's inconsistent. The next one, interesting. You don't do your homework, but you still get to go to the game. Well, that's unexpected, but it still gives the true because the original statement was if you do your homework. Okay, if you don't do your homework, you might not expect to go to the game, but you can still go if somebody lets you, so it doesn't say you can't. Okay, so that is maybe unexpected, but it does get a true. This one here, a bit more obvious. You don't do your homework, you don't go to the game. That's consistent. So this one here is just, I guess it's like not, if it's not inconsistent, then it gets a true. This one here was the inconsistent one. Okay, because it said if you do your homework, you will get to go to the game, but they didn't go. They didn't get to go. So that is inconsistent. The others are not inconsistent. Last part of the video expands on implication. It's called equivalence, and you can see the symbol. Perhaps you've noticed it's like the implication symbol, but it's actually got arrows on both sides there. And so what that means is P implies Q and Q implies P. So it has to satisfy both to get a true, otherwise it is a false because it's got and in the middle. Okay, the conjunction there. It's often also referred to as if and only if, which can be written as IFF. So if and only if. Okay, which is stricter than just if then. So we can see by the symbol that both imply each other. P implies Q and Q implies P. It's both. Okay, and you need to remember how we deal with and you have to have two trues if two things are conjuncted together, and if they're both true, it's the only way the whole statement is true. Let's have a look at it from that earlier table by extending. So just to save a bit of time and energy, I've decided just to extend on our Vlad table, and I will now put in a column Q implies P, alright, and then the final column will be P in equivalence with Q. Now don't get it mixed up with logically equivalent. That's the output of a truth table being the same as another one. This is equivalence. P is in equivalence with Q. So P implies Q and Q implies P. So let's have a look. So we've got implication here. Just the order is different. So we start on the right and we start looking to the left. So true implies true is true. So it's the same forwards or backwards. We read from right to left. False implies true. False implies true is the unexpected one. True implies false. That's the so-called betrayal, the inconsistency. So that one's the false. False implies false is the same as P implies Q. And we see instead of TF, TT, we have TT, FT. The last one here, equivalence. So we have to undergo and for both this one here and that one there. Likewise, this one here, that one there, this one here, that one there, and this one here in conjunction with that one there. So we have T and T, which is T, F and T, which is F, so we need to have two trues. T and F, only one true, so that's false. And T is a true. So that is the standard result for P implies Q, or if and only if. So if we use the Vlad one, where if Vlad has a phone then he can message his deputy, P implies Q, as we had there before, is different to if and only if. So if then and if and only if. So this would be like saying here, if and only if Vlad has a phone, then he will contact his deputy. Okay, now there was the one case where he did not have a phone, but he could still contact his deputy. There's that one there. Alright, no phone will contact, he might have used some other phone. This one is if and only if he has a phone, not using somebody else's, so it is stricter. Okay, so that's what if and only if means. Okay, it's one to take away for homework. Try this one. Proposition P, I passed the exam. Proposition Q, the exam is easy. So P implies Q would be, if I pass the exam, then the exam is easy. Try and do the implication truth table, and also try the equivalence truth table, and the statement for that would be if and only if I pass the exam will be easy. Or the exam will be easy if and only if I pass the exam. Try the truth table for both of those. See you in the next video.